Mr. Mostafa Hagag. Also, please let me talk about the incoming courses that we're gonna have with MegaPlus. We're gonna have two courses. The first one that you can see in your left hand, it's borehole wetland image processing and interpretation. We're planning to start this course on August 9. So if you're interested in this course, please just contact us. And also we have another one, which is practical and theoretical geomechanics for subsurface applications. So if you're interested in one of these courses, please send us a message through WhatsApp or a message also through LinkedIn. As I mentioned today, we're going to be with Mr. Mostafa Hagag. The workshop is case hole logging, and we're going to have this workshop for 2 days. Mr. Mostafa Hagag, he is a petrophysics consultant and instructor with over 38 years of experience in the oil and gas industry. He began his career with Gulf of Suez Petroleum Company in Egypt, and where he worked as a well set geologist and petrophysicist for nearly 15 years. Currently, Mr. Mostafa provides specialized petrophysics consultancy services and delivers professional training courses across a wide range of petrophysical topics. Mr. Mostafa Hagag, welcome to our workshop for today.
Thank you, Sarah, for your introduction. Good afternoon. I will give you an introduction to case hole logging. Okay. Case hole logging, and the workshop or this webinar will be for two what happened? Do you hear me?
Yes, now we can hear you, and also we can see your screen. Thank you.
Okay. Okay. How can I hide this bar in the top one? Okay. Now, introduction to case hole logging. This workshop will be for 2 days. Today, I will talk about cement bond log and the corrosion, and tomorrow, inshallah, I will discuss the production logging PLT and saturation behind the casing. Okay. Okay. The outline of this course today, I will give an introduction to cement bond log, cement evaluation log, and then corrosion evaluation log. Then tomorrow, production logging tools and monitor saturation behind the casing. Did you see these slides clearly?
Yes, we can see it.
Okay. Okay. As you know, the oil field life cycle started with, just a minute, pointer, laser, started with exploration phase, then appraisal and development, production, and then abandonment. So so there are two major milestones: development and production. According to Mr. 𝗪𝗀𝗻𝗀, he says if you cannot measure it, you cannot manage it. So now, on what basis we will develop these fields to produce and develop these fields? So we have to measure it, we have to characterize, and then after that we can manage it. This is the integrated reservoir characterization and management workflow. Okay, this is my suggestion. The reservoir characterization and management started with reservoir description. You describe your reservoir in context of so geometry, size, position, and location, shape. Then what is the properties do you have in this reservoir, like storage capacity, flow capacity, lithology, mechanical properties, connectivity, fluid types, scale. This can be delivered or can be driven from scale data, and then contents. So you have gas, oil, water, whatever you have. After that, if you describe your reservoir very clearly, you will understand the performance. For reservoir, for the field development and the management, the main steps or the main parameters you are looking for, you all the time, all the company will work on it. It's sustain production and maintain pressure. If you have the performance, if you understand or if you work with the performance very well, you will have proper monitoring and management process. This means that you will monitor the change in water saturation behind the casing and the zonal distribution. Okay, all the results will be updated, and then all these results also will go for 3D model to optimize the development. When you say development, either by new wells or by EOR, then update the results. All these updated results, we can update the reservoir description and go again for the same do loop. Sarah, I have a frame of yellow color. What is this?
Excuse me?
I have a frame on the screen with yellow color. What is this?
No, here in your presentation, you see your screen, which is white, and we can see all the maps saying
Okay.
petrophysics deliverables, operations.
Yeah, you don't see it. You don't see this green one. This
No, no, we don't see
okay.
anything green.
Okay. Okay. So the petrophysicist can deliver in the process of the characterization and the management. He can contribute in operation, surveillance, and the studies. Okay. For the operation, for the drilling, while the drilling the wells, use via the open hole interpretation and acquiring data, and also well integrity, cement, and corrosion. And we will talk about this today. For surveillance, we are monitor the you can deliver in SW change behind the casing, zonal contribution and the production problem, and EAR. This is also we will talk about monitor water saturation and zonal contribution by tomorrow. Then in the studies you may have geological model inputs, EAR, all these activities the petrophysicist can deliver or can contribute on it. Geological modeling, EOR, seismic inversion, geomechanics, unconventional, and so on. Cement evaluation log. Okay. Yes, okay. Before I start with this one, for the people who don't, maybe they away from the logging activities or this discipline, what is the log? The log, it is a plot of measurement of one or more physical quantities in around a well on the x-axis versus the depth or time, or both on the y-axis. The term comes from word log, used, okay, used in as a record or a note. This is, as you see, this is a plot of y versus x. X is any physical property, and y is either depth or time. In case the whole logging, the tool can be run on wire line in case of the vertical hole up to 55 degree, less than 55 degrees hole deviation, or coil tubing for horizontal hole, or with the well is deviated more than 55 or horizontal. And then tractor in highly deviated hole 55 degree, and it is higher than 55 degrees, and mainly in the cased hole. Okay, what is the well logging objectives? Open hole log. In open hole, this is, I think, we know that we use the open hole logs for formation evaluation and reservoir characterization, lithology, shellness, bed depth, thickness, porosity, permeability index, water saturation, fluid contact, formation pressure, fluid sampling, formation image, and seismic calibration. In case the hole logs, we have mainly three main objectives. First one, we can monitor the water saturation change behind the casing by using the generic name, or what call it TDT, thermal decay time tool. Zonal contribution and production problems diagnosis in PLT, and borehole casing integrity and condition, cement and corrosion. The log data acquisition strategy in while the field life, or during the field life. If you have production on x-axis versus time on production on y-axis versus time in x-axis, and the exploration phase started with this is the red one is the number of drilled wells. As you see in the exploration phase, we have higher number of wells, and mostly it's open hole. And then we slow down the number of wells and almost flat and then the field started to produce. We have secondary and tertiary recovery, and in this case we have mostly cased hole logging, either PLT or TDT or even corrosion if in case of any problem, till we declined. In declined and abandonment, we usually run corrosion logs. Okay. There is an important note here that much of the information acquired at this time is difficult or impossible to obtain later. So when you drill a well, if you don't get the needed data, you will lose it forever until you pay it for another well to have this data. Okay, this information can be critical for the field development and exploration. Okay, well logs, well stages, we have drilling. We start with the drilling wells. We have landing, geosteering, and formation evaluation in open hole logs, either a wireline or LWD. Then we run logs. So we drilled, then run logs for formation evaluation, then run casing and make cementing, and then we run cement bond log and well integrity, or cement bond log mainly. And then production. Okay, so while the production, we usually run the surveillance logs like RST or TDT and PLT. Why cement evaluation is logging? Now we will start to talk about the cement evaluation log. First of all, the first objective is to evaluate zonal isolation, zone to zone isolation, casing cement isolation, cement formation, cement distribution behind the casing to ensure corrosion protection, identify the top of the cement. Okay, evaluate cement remedial jobs. The physics of we have three physics for cement bond log evaluation. Temperature, it's in all days. Okay, acoustic and ultrasonic. Temperature log. Cement hydration, when you put cement, when you cement the well, and then leave it for many hours, usually 72 hours, to set the cement. Set meaning that to hydrate or to be hard. So cement hydration is an exothermic process. When cement set, it is release heat. This thermal signature can be captured by temperature loss. This is in all days. Okay, not now. It is all days. Temperature temperature anomaly. It's sudden increase when you have an if you have the top of cement here, you will have, as you see, the temperature is about 110, and then suddenly it is over 125 or 120. So the top of cement here, it's at 300, 710 or 20. Okay. Time sensitive. This survey is most effective 4 to 12 hours after cementing before the heat dissipates. Okay. Sonic. So now as I said, we have three basics or three physics for the cement evaluation. First one is temperature in all days, not used anymore. Okay. And sonic, on sonic basis, we have three curves: CPL, VDL, and transit time. Cement bond log. This is the tool, CPL VDL tool. Okay, it consists of transmitter and two receivers, one on 3 feet and the other one for 5 feet. So what happened when we send a sound or a signal? So it will go through the casing to the two and received in the 3 feet, and another one in 5 feet. So these signals or this sound, it passes through casing and cement and formation. So CPL, which is the cement bond log, it's amplitude of the first arrival in millivolt. So the amplitude of the first arrival, okay, the amplitude of the first arrival, it will be recorded. This is the amplitude. It means the height of the wave. Okay, so the amplitude of the first arrival in millivolt, measured at 3 feet. It is a function of casing cement bond. So this is the casing and cement. If it's high amplitude, it meaning it is go through the casing, so there is no cement. And if it's low amplitude, it means that you have a cement behind the casing. VDL, you have you receive the signal at 5 feet, and also it goes through casing, cement, and formation. So the VDL is the responding to the interaction between formation and cement. Okay, this one is not amplitude. This one is a wavelet. Okay, okay. So okay, it's 5 feet receive for VDL analysis, allow easy differentiation between casing and deformation. Okay, so this is a as you see, this is a VDL looks like. It looks like a microseismic or something like this, or seismic like this. So we have troughs and we have peaks, and we have black and white in between these ones. Okay, so if you have casing, you will have this one as a straight lines, but if you have the formation, it started like this. Okay, transit time, it's time elapsed for T0 to the first arrival from here. This is called the transit time. It's used as a quality control indicator. CPL VDL presentation. As you see, this is a sample of the CPL VDL. This is the amplitude. Okay, so transit time here, this one, it's used for quality control. Okay, and CPL, this one, the amplitude of this one of as you see here, it's have a good cement. Here have a, if it's high amplitude, it means that it's you have free pipe. If it's low, it you have a good cement. VDL, variable density log, and as you see here, this is like seismic, but it is if it's have the shape of the formation, it means that it's you have a good cement. Okay, so for this, because of this is a sonic tool, so there are some quality issues should be considered, and we can capture this the quality of the log from the TT curve. If it's irregular TT curve, it's the tool eccentricity or poor contact. There is a problem in the tool eccentricity. TTT cycle skipping, there is, if you have cycle skipping or of value of higher than the normal, a strong cement bond. TT lag formation arrival, poor cement to formation bond. Okay, if you don't have a formation arrival, you will see the poor cement to formation. TT matches casing only, which is about 57 in the delta T. It is free pipe or microannuals. Because of this is the SCPT2, sorry, the CBL VDL, the normal sonic tool, it is not covered all. It's read as a bulk volume of around the tool. But here, it is the segment. Some companies uh, introduce another technology that which is we have a transmitter and the receiver in 6 pads around the borehole to have more coverage, and we can so we can make a better uh, cement evaluation. Measure the cement. This tool is called the segmented bond tool SBT of Baker Hughes. Measure the cement bond integrity in 6 angular segments around the casing. The SBT surfaces can find and define a channel in the cement. So because if it's have covering more area in the casing, so we can have, if there is a channel, or the channel means that it's a part of the casing of the cement has no cement in it. So behind the casing there is a piece of an or area have no cement on it. So this is called, okay, in the annulus, channeled in the cement annulus, which could okay, result in hydraulic seal. What is this? It's okay, which result in a poor hydraulic seal. The acoustic transducers are mounted in 6-pad position in contact with the interior casing wall to provide compensated attenuation measurements. Okay, so we have six curves instead of one, and we have minimum and the maximum uh, uh, amplitude. So these ones, if it's are the same, it means that it's we have a good cement, and there is a difference between them. So we have a channel in the case, and also it can provide a cement map in addition to the VDL. Okay, and as you see here, this is an example, and the first column is gamma ray, and delta T maximum and the minimum, red and the blue, which is filled in between. Second column is attenuation of 6 pads that cover 360 degrees of casing, not sector as a some believes. Third one, average and the minimum attenuation, green and the blue. Fourth column, cement map, and then the right column, full wave VDL. Okay. 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 CBL amplitude. I have this. Okay. CBL amplitude interpretation. As you see, what is needed? Okay. Expected cement impedance amplitude for 100 bond E100. Free pipe amplitude it's E free, and the measured amplitude E measured. So we the interpretation, one of the interpreted curves from the CPL is what's called bond index. Bond index is this log log 10. It's E measured over E free divided by logarithmic of E100 over E free. So this cement bond, it's the bond index is an indication of the how is the quality of the cement, how is good or bad. Okay, it's conventionally we are looking for B or the bond index from 80 to 100. It will be good cement. Less than 80, it is questionable. Bond index is qualitative indicator of a channel. A bond index of zero point 0.3 suggests that only about 3% of 30% of the annulus is filled with good cement. The minimum cement interval at 80% bond required for cement hydraulic isolation is shown as in the plot. Okay, one of the objective of the cement and the main objective, actually, if we have two reservoirs, we wanted to isolate between them. So this chart gives you the minimum cement thickness needed for isolate the reservoir. If based on the casing diameter. So if you have 7-inch liner, so you at least need 3 meters. Okay, 3 meters at least, about 9 feet cement thickness to isolate between both reservoirs. So less than 9 feet or 7 feet, 6 feet, this will be damaged in very near future. So this is just a guide to see to just to tell the drilling that I need 9 feet of cement thickness between a good cement with no channels between the two reservoirs. Sorry. The minimum cement interval 80% required for cement hydraulic isolation is shown in the plot. If we have, say, 9 and 5 inch casing, so we need at least four, 4 meters, about 12 feet of good cement between the two reservoirs, and we call it hydraulic isolated reservoirs. Otherwise, they have to do a remedial action. Okay, this is just a guideline for the interpretation for the CBL bond, okay, CBL and the VDL. Free pipe, its CBL will be high, attenuation amplitude will be very high, and the casing arrival is strong, very weak. Okay, and this is all the conditions for the if you have a good bond, casing swimming low, weak, and strong. So good bond, casing to formation low, weak, amplitude low, casing arrival weak, strong. Okay, and here there is fast formation high, swamped by formation signal and strong. So all these guidelines, I will show you some examples from it. The other technology is, and we talk about temperature as a physics, sonic as a physics give you an amplitude and VDL, and then ultrasonic tool. Ultrasonic tool, it is not, it is, we use ultrasonic transducer or source for source. In sonic, we measure the signal across the radial of the tool. We mean that we have receiver here, we have transmitter here, and we have two receivers. So along this one, this tool, it is not like this. This tool is just a transducer, send ultrasonic pulse and return it back. So this is based on the radial, like radial concept, not axial concept. Okay, so ultrasonic image tool transducer. An ultrasonic transducer emits a beam at 200 and 700 kilohertz, spin about 707.5 rotates per second, 300 and scanning of the casing. So this is one, it is covering all the casing. Cement bag around the casing. We have two operation, and this is, and I wanted you to imagine that this is a transducer. This transducer send beam or send the ultrasound to in this direction. This one is called flow velocity mode, and can measure the property of the mud, and give you an acoustic impedance, which is called Z. So it can give you the acoustic impedance of mud, and then it's rotate and send to the formation, to the cement or the casing and cement, and measure the acoustic impedance of this one. So now we have these two. This transducer is rotate, give you sound in this direction, and give you another one in this direction. This one is called for fluid property mode called fluid velocity, mud velocity, and give you acoustic impedance in this direction or for the mud, and measurement mode give you amplitude, internal radius, thickness, and acoustic impedance. So this one, the measure give you amplitude, internal radius, thickness, and acoustic impedance. For the different casing sizes, we have different transducers fit with this casing size. Okay, what is the principle of measurement? If you have, we have a, and we will talk about the signal or the pulse towards the casing and cement. What happened? An ultrasonic transducer emits a short acoustic pulse, most of the reflected back, while the remaining energy enters the casing. So as you see here, it is, he sent a pulse and return it, and most of it return it, and some of them go to the casing and to the cement. Okay, so and reflected, يعني, and it's entered the casing and reflected, and some remains enter the cement and reflect. So we have a wavelet, or we received a wavelet. Okay, so attenuation of this reflection related to the acoustic properties of boundary material, mud casing cement, mud casing cement. So based on the boundaries of this one, the reflection will be happen. Okay, the acoustic impedance of the casing and wellbore fluid is constant, right? So now this is why we run, or we do a fluid velocity mode, to have wellbore fluid is constant, to have the value of the fluid. Okay, so the signal decay in casing depends on the acoustic impedance of the material outside the casing, is cement or fluid. It means that the receiver sees a high amplitude followed by exponential signal. Okay, so we have, so this one from the casing, from the casing, from the transducer to casing, and then some of them come from casing and cement, sorry, from the mud and formation, sorry, from cement, from mud and the casing, and the rest comes from the cement. So he can resolve this one to know all the properties of the cement: amplitude, thickness, and amplitude, internal radius, thickness, and acoustic impedance. A cement map represents the visual indication of cement quality. This is, as you see here, this is the internal casing radius, and then cement map and uh, cement map and the bond index. Okay. Okay. How the tool can know this is a cement or this is a gas or a fluid? So based on a preset threshold or parameters measured before in the lab, and he knows that it's the acoustic impedance uh, of gas. Okay, it is equal, or the water is 1.5, and the acoustic of water fluid 1.5 to 3. Gas is very, very, very low acoustic impedance. Cement slurry is 1.3. Cement lightweight is from 2 to 5. Cement G class or class G, which we are using usually, from 5 to 7. And the steel is about 40. So, or 46, sorry. So he put a threshold for each one, and he collects the data, and he knows based on the threshold he put it, he knows that this is cement or solid or gas or whatever. يبقى the ultrasonic imager discriminate between solid, liquid, and gas dry using acoustic impedance thresholds. Acoustic tools respond to acoustic impedance Z. Okay, acoustic impedance denoted as Z quantify how much the medium resists the passage of the sound wave. The meaning of the acoustic impedance. That is, if you have solid, how much it resists to the sound wave. This is simply the definition of acoustic impedance. It's acoustic impedance is density multiplied by acoustic velocity. So Z is expressed in millirad. Okay, the ultrasonic discriminate between solid, liquid, and the gas derived microannulus using acoustic impedance threshold. I think I repeated this one again. Okay. This is an USI CBL VDL representation, as you see. Okay. Good cement, high impedance. Okay. Okay, sorry. A good cement, this one. High impedance, 6 to 8 millirails, strong damping of signal. Contaminated or light cement, lower impedance, ambiguous signal. Mud or oil, low impedance, weak or delay echo. Gas, very low impedance, minimal signal return after appear as a free pipe. Okay, this is a VDL as you see here. This is a casing. It is not free pipe. We have an formation arrival here. We have an bond index here. We have acoustic impedance minimum, maximum, and average. And as you see here, this is a blue one. It is can be water or can be not no cement. Good cement is blue, is the dark brown one. And also we have a CBL also. This is the amplitude of CBL. Okay, as you see here, this is high amplitude in CBL. It means that it's low. There is no cement or bad cement quality. Okay, and as you see here, we may have an casing arrival in this part. This is a comparison between sonic and ultrasonic cement logging. Very quickly, measured principal acoustic amplitude and waveform, acoustic impedance and reflection analysis. Okay, two configuration: one transmitter, two receivers at 5 and 3 feet, rotating transducer with azimuthal coverage, bond type evaluation, casing to cement CBL and cement to formation VDL, casing cement and cement to formation with circumferential mapping. Resolution moderate. High quantitative impedance at 360. So the ultrasonic is higher. Sensitive to microannulus. Sometimes, what is the microannulus is? Microannulus is just a gap between cement and the casing, very minor gap, very small gap. In case of gas reservoir, this is make a disaster for the production. But the in normal practice, too, if you have a free pipe and the drillers swear that it's a good cement, so we ask them to pressurize the casing just to close this gap, and we run this casing and we will see this. Oh, this is called microannulus. Okay, and required pressure pass to detect. Okay, and detectable Verne impedance constant contrast. So in ultrasonic, you don't if there is any gap, it will be appear on in impedance itself. You have a 360 impedance, so you will see the contrast between these ones. Channel detection limited because it's limited. If there is a channel behind a channel of cement itself, there is no channel, there is no cement on it. It's difficult to find it, but it's in ultrasonic. It's a direct azimuthal imaging of channels. Fluid sensitivity less affected by borehole fluid, require fluid property compensation. Tool centralization critical for accurate TT and amplitude reading, less sensitive due to rotation scanning. Application, routine cement evaluation, perforation planning. Advanced integrity diagnosis, gas migration, casing wear. Limitation, poor in thin cement, cheese masked by hard formation. May struggle in high density mud or thick casing unless optimized. Okay. What is the factor affecting cement log interpretation? Microannulus, I think I explained it. It's a tiny or annular gap between casing and cement, where it will result in misinterpretation. Generally, pressure up casing 5 to 100. This is an important. If the cement is not set completely and you pressurize it and inflating, this will create more gaps. So I think we be careful about this pressurized casing before cement is set. It will create another gap. Okay, it may damage the cement if it's not fully set. To close the gap, if the cement job was good. Ultrasonic tools are less affected than CPL, VDL, and SBT, but in the presence of liquid in the gap, with the opposite effect in the presence of gas. Excentralization, potential concern deviated horizontal wells due to absence of cement. Okay, due to absence of cement on the low side and the small distance between casing and the formation phase. Logging tool centralization is mandatory for USIT and CPL VDL. The SCBT pads with articulated arm and unaffected also CPL VDL. Fast formation. Acoustic signal from some formation reaches the receiver ahead of the pipe signal. Fast formation affects the CPL, VDL, SCBT logs, but don't affect USIT interpretation. Lightweight cement, lack of contrast in acoustic properties between lightweight used in weak formation and regular cement slurry. Cement setting time. This is important one because the drillers usually try to accelerate the non-drilling time, no drilling time. So they said, okay, the cement will be set in 40 hours, 48 hours, and so on. But it's important for CPL interpretation. If the logs is run too early before the cement is set, it may indicate poor bond and an unnecessary squeeze operation may be run. What is the challenge in cement bond challenge? As you see here, we may have casing weld. We may have it will be appear on in casing in log interpretation. Muddy channel in cement. As you see here, there is some muddy channels here, like these ones. And well-centered casing, good bond. Okay, as you see here, this is a well-centered. As you see here, the cement around the casing is good and center, and we have a good cement, right? Wash out in the formation itself. So you may have some mud on it. It will be appearance interpretation. Pipe against formation. Okay. Here, this one, I think in shale, if you have an shale parts, you might have some phenomena. It's called the galaxy, but I don't see it. Galaxy phenomena, which is that the shale is contacted with the pipe exactly. Okay. Mud left in the washout. Okay. Gas invasion. You have perforation. You may have it in old wells, right? Okay. Now this is CBL VDL examples of good log. As you see here, we have a good log, good CBL example. We have an formation arrival. Okay, there is no casing arrival. This is a casing arrival. We don't have it. Okay, we don't have it. So high quality TT curve, it's almost constant. We have a good one. CBL with relatively small amplitude. This scale is from 0 to 10, and also from 0 to 100 for high amplitude. So as you see here, it's very low. It's a very low amplitude. Okay, verify the VDL. No casing arrival, lost of formation arrival. Okay, and here TT is, as you see, it's errated TT. Okay, CBL VDL high straight amplitude, as you see here, and this is the colors, by the way. It means that it sees the casing and its color. Okay, okay. There is casing arrival and very weak formation arrival, and as you see here, this is the colors, not like this one. Okay, here, as you see here, the casing, we have a casing here, this casing arrival, and as you see in some parts you have fast formation. It's passing the casing arrival. So in case of good cement and the formation slowness less than steel, okay, 5 microsecond per foot, formation arrival, okay, arrival first, okay. Transit time shorter than casing arrival. The transit time and CBL amplitude will be affected. High CBL amplitude in areas of fast formation arrival, no CBL evaluation is possible. Okay, this is another example. Okay, as you see here, we have a good bond, we have low amplitude, okay, and we have weak formation arrival, but we have a channel. Okay, as you see here, we have a channel. Okay, so this channel can be from acoustic impedance. We have minimum, maximum, and most likely we have it should be the three. If it's a good bond, the three is read the almost very narrow or very close to each other. But here, because we have a seam, we have a channel. It's so this is we have this difference. Okay. As you see here, we have an okay example of behavioral correlation. Okay, look at this one. This is this is amplitude of CBL. As you see here, we have a very bad cement here. Okay, with almost we have close to casing arrival, and we have a good cement in the rest of this one. Okay. Any questions? Yeah. No.
Yeah, hello, Mr. Mustafa. I have a question here.
Yes,
Can you hear me?
I hear you.
Yeah, great. So, when as you talked about the bond index. So you said that when we have the casing size, so from if we plot the casing size with the depth or the distance that we have to do the casing or the cementing. So for example, if my formation is like very, the sand and shale thickness is very small. So in that case, what should be the minimum requirement of the cementing?
Okay, now if I understand your question, now we have a cement bond. It's about 80%. For the isolation, we need, say, 8 feet or 9 or 10 feet. That's right?
Right, correct.
So what's your question?
So when my formation, for example, if I have a two reservoirs which is differentiated with the shale, we have two sand. For example, in top we have the shale, then we have the sand, then shale, then uh, shale. Means it is a sand shale sequence. But my thickness of the sand and shale is very less, and we are producing from these sand reservoirs. So in that condition, what should be the minimum thickness for the cement?
Based on the casing size. If you have
Yeah,
7 and
yeah.
according to, okay, based, it's
Yes,
not,
yes.
first of all, this is used in case of, we have a differential pressure between both, big contrast in pressure between the reservoirs. Right? Hello? Hello?
Yes.
You know?
Hello. Yes. Can you hear me?
Yes, we can hear you. You can make your question.
Yes. Any questions? Can I continue?
Yes, please, you can continue.
The other hear me or not?
I think you can continue, and if somebody else have a question, you can write it in the chat section. But Mr. Mustafa, you can continue with the presentation.
Okay.
Thank you.
Okay. Welcome. Okay. Now we finished the cement bond log, and as you see, it is crucial. But I tell you, my experience in via ADCO, because I worked in ADCO for many years in Abu Dhabi in UAE. Because of the cement bond log is expensive, and we waste a lot of time on for waiting, and also we don't make any remedial action for very long time. So what is the company decided to put some criteria for the cementing process. If this criteria is fulfilled and as per textbook, so we don't need to make a cement bond log in every well. Just make a random test or random check and to see is it good or not. Okay. My question is, what is the challenge with lightweight cement? As I mentioned, that it's a lightweight cement. You cannot differentiate it between, is not characterized with the tool at that time. Okay, so lightweight cement, it's you don't is it you don't know if it's fluid or lightweight. That's it. Okay. Okay. Now we can go for the second part, which is the corrosion logs. Corrosion overview. What is the corrosion is? Corrosion is the deterioration of a substance, usually metal, because of reaction with its environment. Corrosion occurs in three classes of processes: electrochemical, chemical, and mechanical. Electrochemical, it's galvanic when two dissimilar metals are electrically connected in corrosive electrolyte. Do you imagine that it's galvanic? It's one of the major problem when you have, say, one well with casing in onshore, and you have another well with casing, and you connected with them a pipe, so it's working, and you have water or fluids in the underground, so it's working as a battery actually. So this is making as a like an even there is a technology is called cathodic protection. So this is caused uh, galvanic corrosion. Okay, so this just an example. Crevice, it's a localized corrosion. Is in shielded area like under gasket or deposits. Pitting small deep holes from due to localized breakdown of protective films. Chemical, if you have sour H2S, hydrogen sulfide causes brittle failure in high strength steel. CO2, carbon dioxide react with water to form carbonic acid, attack the steel casing. Acidic, from low pH fluids, often induce thermal or injection wells. Bacteria, caused by bacteria, especially sulfate reducing types. Mechanical, ممكن stress cracks form due to tensile stress in a corrosive environment. Erosion, metal loss due to high velocity fluid flow combined with the chemical attack. Factor that affect the corrosion are corrosion rate include exposure to fluids, pipe metallurgy, and temperature. Corrosion can be internal, external, or both. Okay. Its distribution either it's general, uniform, or pitting. So the corrosion is just you measure the corrosion logging is used for to monitor the rate of deterioration of the casing by time. Okay. Factors that affect corrosion rate include exposure to fluids, pipe metallurgy, temperature. Corrosion can be internal, external, or both. Its distribution, uniform in nature, general, localized in nature, pitting. As you see here, if this is a tubing, and this is one casing and another casing. So you may have inner casing, external corrosion in the inner casing, and you have internal corrosion in the inner casing. May have external corrosion in the external casing, and internal corrosion in the external casing. Okay, and so on. A corrosion evaluation tool principle. We have three main physics for the corrosion evaluation. First one is the mechanical. Second is electrical and electromagnetic. Third one is ultrasonic. The mechanical one is just multi-finger calipers with 24, 40, and 80, and 24, 40, 60, and 80, based on the size. Okay. So this one just caliper touching the inner diameter of the casing and measure the diameter itself. That's it. And from this one, we can map or we can see what is the reduction in casing or the increase in diameter or the corrosion, the corroded parts. Identify internal metal loss from corrosion, erosion, or mechanical wear. Measure the minimum and the maximum internal tubing or casing diameter. Locate casing collars and diverter valve tools. Identify casing joint with the different weight or wall thickness. Locate collapse or hole in casing. Distinguish between parting and split in the casing. It can be 24, 40, 60, and 80 fingers. Here, as you see here, we can have a severe casing damage associated with the perforation. Okay, here is a perforation. And as you see here, we have severe casing damage. And this is the calipers. Okay, and we have an example of corrosion. We have a metal loss in 2010 with the 2009 with the black one, and we have the metal loss increases in 2010. Okay, and this is the metal loss rate. Okay, 1 millimeter per meter. يعني you have 0.8 or 0.8 millimeter per year. Okay. The electromagnetic tools. This tool, it is called, where we usually run the electromagnetic tools. We call it MTT BAT. Okay, the BAT tool is pipe analysis tool. What is the pipe analysis tool? The tool has the tool has upper and lower arrays. Upper and lower arrays. Each contains 6 pads. Each one have 6 pads, like FMI, which are oriented to assure 100% coverage of the casing. Okay. Each pad contain pair of coil of measuring both flux leakage and eddy current. Okay. The electromagnet in the sonde is the source of the magnetic the electromagnet in the sonde is the source of magnetic flux. The tool was designed to maintain equal flux density for the casing size, but it will be distorted in the vicinity of both an external or internal. The high frequency 202 kilohertz eddy current is generated in same bed, which induced a circulating current at both 1 millimeter in depth into the inner casing. The damage of the internal casing surface affected the distribution of the include. This tool is simply, it have a electromagnetic source, measure the magnetic flux. Okay, and this magnetic flux is constant whenever the thickness it's modeled to have the thickness. If the thickness is constant, the magnetic flux is constant. So if the thickness is reduced, the magnetic flux will be distorted. Okay, so this magnetic flux, it give you a total damage or total metal loss. In the same time, we have a source of eddy current, push a current in 1 millimeter in the casing, and whenever the eddy current is good in case of the inner diameter is good. Okay, so if any damage in the inner diameter, it will distort the eddy current. So this one give you total metal loss, and this one will give you only the inner. So if the total is not good and the inner is good, so it means that the corrosion is external. And if the total is not good and the eddy color is not good, so it means that it's the uh, the corrosion is internal, right? In case of hole, both of them give you very high damage or very high response. Okay. Okay. So according to how many the eddy current defect diameter, if it's and all and now they are measured and scale it. Okay, if it's a half division, okay, it's equal to 12 millimeter. Two divisions, it's 18 millimeter. 4.5 division, it's 24 millimeter. Flux leakage and so on. Half division, 10%. One division, it's 20. Two division, it's 40. Three division is 60. And four division, it's 80 to 80. So he measured this one and scale it on a log or in the plot, and he can measure how much the severity of the corrosion. So if there is if less than 20%, so this one is rate 0 or there is no rate on it. The corrosion is rated is presented in rate or code according to the severity. So if the 0 to light magnetic anomalies, so indicator of limited corrosion less than 20% penetration. Rate 1 or code 1, light to moderate magnetic anomalies indicating of corrosion corresponding to the 50% penetration. 2, moderate to severe magnetic anomalies indicating of corrosion corresponding of 50 to 100% penetration. 3 is extreme magnetic anomalies indication of extreme corrosion. Okay. This is the presentation of PAT log. As you see here, we have an eddy current upper array, eddy current flux leakage upper array, okay, and eddy current lower array, and flux leakage of of lower array. As you see here, okay, this is they put it in this presentation. Flux is blue, one division. As you see here, it's 1, 2, 3, 4, 5 divisions. Okay, below one division indicating resolution if less than 20%. Log shows significant eddy activities less than one division, indicating generalized internal pitting up to 12 diameter, the 12 millimeter diameter or internal scale. Okay, so from this one, from this division, he can, and according to the code, we will know the severity of the corrosion itself. Okay. At 113.19, there is a bit of 50%, this one, penetration, and is external, because the flux, the flux give it 50, and the inner give it 0, so it's external. At 1322.5, there is a pit with 35% penetration, and its external joint is considered code 1. So according to this one, and according to the table, it is okay, code 1. At 1331 has maximum flux response of 3.6 divisions or 75%, 70 to 75% penetration. Defect is internal with equivalent. Okay, as you see here, the flux is we have a flux showing, and the eddy current shows, so it is internal one. Okay, and according to the division, it's 12 millimeter, 12 to 18 millimeter joint, and consider code 2. Any question here? No?
I think we don't have questions for now.
And all the people, all attendees hear me, because there are some people who don't hear me, huh?
We can hear you.
Okay. Okay. Now we will go to what happened. Okay. This is the bat log in recent days. Log shows significant flux leakage and eddy current. Eddy current is here, and eddy current is here, and the flux leakage is here. So pattern show up to from 74 to 74.5 this part. Okay, the pattern are show less than 20% penetration. Okay, but appear to be a man-made, as you see here. This one, it's showing on eddy current the flux leakage. So this is man-made and probably related to a pipe manufacturing. There is a problem in the pipe manufacturing internal. There is some in the casing, right? So an internal part. Okay. Second tool is called multi-frequency electromagnetic thickness tool. Okay. Sometimes you need to detect if we have 3 or 4 casing. Actually I have don't encourage this to see the third casing from outside, or the third casing from inside, to see the corrosion, because if the 2 casing are good in it in if the casing is good in the inner part, it's no need to see what is behind the third casing. It is okay. You can do it, but it's I don't think in a very important issue. So for the detecting of large scale corrosion, such as thinning, hole larger than 2 inch, and vertical split, detect metal loss in the outer casing of multiple casing. So in case of you have rupture or have a damage, complete damage of the outer casing, yes. But otherwise, I don't think it will be help. Anyway, a coil generated an alternating magnetic field that interact with the casing. A second coil measures the field phase shift, which is related to the 3 casing property: magnetic permeability, electrical conductivity, and thickness. If the first 2 are known, then the thickness is known. So it make a magnetic field, and you are receiver and you have transmitter and receiver. So it measures the phase shift. So unless if you have any distortion in the phase shift, it means that you have different in thickness. Okay, the same as flux leakage in the pad. An internal electromagnetic caliper measuring here you don't have eddy current. You have electromagnetic caliper, not have eddy current. Is made so as any thinning can be defined as being either inside or outside casing internal diameter. Unlike mechanical and acoustic caliper, it is not sensitive to mineral scale up, provided that the deposit's material is non-magnetic. So here you have you have electromagnetic caliper, and this it show you the internal diameter, and the magnetic field, the phase shift, show you the total thickness damage. So from the internal and the total, you can see is it inside or sorry, this is in internal or external corrosion. Here is the raw data, the tool, the log presentation, MTT log presentation as a raw data. Okay. Okay, and here is the interpretation of it. Okay. Okay. So external metal loss. This is another example of METT. External metal losses of approximately 20% here. The internal caliber does not change over the defective. It means that it's external. Here is the caliber, as you see. Okay. And the outer one, this one is, as you see, have an external corrosion. External metal loss of approximately 30%, as you see here. The internal caliber does not change over the defective internal. Okay. So the inner diameter doesn't change. Also here we have a metal loss about 30%. Okay. The third tool is the ultra corrosion imager, is UCI. It's the same concept it's the same physics as uh, USIT, which we explain it in cement. So it's the same basic tool, USIT, based on the open hole imaging. It is used for cement evaluation, casing geometry, and the casing corrosion. But this one, the transducer, is high frequency focused more. It have more focusing on the target. Okay, so this is the UPI, which is USI, but it's for the oil-based mud, and here for the USI. لا, sorry, UPI, it is all for. Okay. So this one is USI, which is a flat. The transducer is flat, but here we are focusing and more higher frequency. Okay. So USI is high resolution internal and external casing corrosion and damage analysis. Cement USI is cement evaluation, but baseline internal and external corrosion and damage analysis pipeline inspector. This is secondary application. So you cannot run USI for corrosion. But by the way, if you run cement bond log, you can run a reference corrosion log for the future to make a time lapse. But you cannot run USI for corrosion. You run CI, but you can run UCI for corrosion. There is no cement on it here. It's only for corrosion. USI, it's cement and a secondary for corrosion. UBI, it's open hole imaging, internal casing and corrosion. UBI is open hole. Okay, open hole damage. Oh, yes, in the open hole in oil-based mud. Okay, internal casing corrosion and damage. So it's the same. The USI transducer is especially designed for corrosion evaluation and application. The other two have secondary corrosion application that can be exploited in the same run in the hole as a primary measurement. Okay, so we emit a signal, and it is also we have an reflected from the casing and from the cement, and the two peaks it can give you the casing thickness. Okay, it's the same exactly. We have a fluid properties, we have measuring mode, and we have a fluid properties mode. Okay, and it can give you internal radius, internal rugosity, casing thickness, acoustic impedance. This is the UCI log presentation. Track 1, main echo amplitude image corrected for eccentricity. Dark color indicate low amplitude due to internal rugosity, corrosion, or damage. So this is an echo amplitude image. Okay. So track 2, main echo amplitude curves, minimum, maximum, mean, tool eccentricity indicator. This one for the eccentricity indicator. Track 3, internal radius imaging. This one. Calculating as the difference from mean at each depth. Corrosion or damage, dents, like this one, is red. Okay. Deposits, IE bumps are blue. Light red blue pattern are an indication of manufacturing variation and or normal. So the blue one is good. Okay. Okay, the corrosion or damage is red. Okay. Deposits are in blue. Light red or blue pattern are an indication of manufacturing variation. So this is given an indication of the internal diameter, internal radius. Okay, internal radius curves is this ones, and then thickness map. Okay, the track 5, thickness image computed as a difference from the mean and each depth. Reduced thickness is red. This one is reduced thickness is red. Light red blue pattern are an indication of manufacture variation. Doubtful thickness data are automatically blanked. If he cannot recognize anything, he will put it as a if he cannot recognize the thickness or cannot calculate the thickness, he make it on white. Thickness curve minimum and the maximum, okay, shaded are shows in average thickness. Okay. This is the ultrasonic interpretation, okay, presentation. Tool eccentricity, track 1. Internal metal loss image, okay, as a percentage of nominal thickness. The metal loss is computed from the measured internal radius and the nominal casing. Light blue indicating losses less than 25%, yellow and red increasing losses as usual. This one, okay, losses. Okay. Next 3 is internal metal loss curve, minimum and maximum, and then total metal loss image indicated as a measured thickness as a percentage of nominal. Okay. Light blue indicate less than 25%. Okay. So this one is internal radius. This one is the thickness. Okay. So from both, we can see if it's internal or external. Non-valid thickness measures are automatically. Thickness metal loss curves, minimum, and maximum. Minimum, mean, and the maximum. Maximum loss curve is the maximum of internal and external losses. The thickness image is here is an example, is clear example. For the USI log example, the thickness image is blanked out along the groove and across the joint because a reliable thickness measurement cannot be made there. The casing must be a good condition internally to make a good thickness measurement. The USI log at its normal vertical scale of this is a bigger scale, shows a small patches of internal corrosion just above the joint and is reduction in casing thickness due to the threads. Okay, as you see here, this one we have a problem here. This is a thread of the casing, so it shows some corrosion on it, and this is a cable groove. Okay, and we have a casing with different weight, okay, and this is a manufacturing variation, and the thread here show some corrosion above the thread. This is another log example. There is a large hole around 2000. This one big hole. The hole is more than 10-inch high and 5 wide. There is an indication of scale deposits and severe corrosion in the whole interval. Okay, this is severe corrosion, as you see here. And also, as you see, we have 4 shoots per foot perforation here. Okay, thank you. Now we open for questions.
If you would like to make a question, please open your microphone and you can make the question to Mr. Mustafa.
And if possible, it's easy, can write it.
There we have a question in the chat section. Mr. Mustafa, if you can answer it.
Yes.
So one of the question is there a special tool to evaluate lightweight cement?
Yes, we have an yeah, the USI, but it should be characterized by the vendor. He take a sample, he take from the light lightweight cement and send it to the lab and measure the acoustic impedance of this lightweight and to differentiate between the slurry. So it needs to contact with your company, with your logging company. Okay, US, I remember that it's when we are in started this lightweight long time ago, 15 years or something like this. So it's we sent this to the lab and he adjusts the tool to read it if they use it. Okay.
Thank you. Okay, so thank you. Thank you all for
There is
attending
a
to this.
question.
Yes, oh wait,
Yeah.
yes.
You are in hurry, Sarah?
Uh,
Yes, it's here. I show you that it's magnetic tool. I think yes, it's if this perforation is big enough, okay, because the resolution, as you see, this corrosion is not too small. If the perforation is يعني have a good intensity in it, I think it can, yes.
okay, I think we don't have more. Okay, there we have one more.
Is this a corrosion effect on permeability? No, it's the corrosion. It is the corrosion is it's in the casing, in the steel. The permeability in the reservoir. But if you have some corroded, you have a damaged casing. It means that you might have some reservoirs. It is open on each other, right? Okay. Oh no, yeah. This PDF you can contact with Sarah with the mega solution. They can provide you with the PDF, no problem.
There we have another question. It says, being a geophysicist, what are the main role in case hole logging?
Usually, the geophysicists uh, work on in the field either before the drilling to define the wells where we will drill, or while we drilled, we update the cross section. Okay, so if you have a problem in say in corrosion, you have water breakthrough in one area, and they told you that it's come, we have a water breakthrough, and you worked extensively on the seismic, and you find that it's no way we cannot have this water breakthrough in this well unless we have a corroded casing in another well and it is channeled behind the casing and go to this well. You have to understand this. But if you don't understand this, so it's you have lack in experience, lack in knowledge. No need just because you are geophysicist, so you are not concerned with corrosion. No, the oil field is a small pool. We have to know everything on everything, and you have to specialize in one thing. Okay. Do we need to share the cement slurry data casing with the logging company before running the cement evaluation? Yes. No problem. We are in, okay. We are not hide and seek. We are in one team. If you know that this is a company, he knows the slurry, the mud engineer, the cement engineer should deliver the data to everyone. But yeah, no problem. Okay, be open mind. Don't hide any data unless it is confidential with the company, like production, like perforation, like something very high strategic. But it's the operation and cement and so on. Unless you are not in confidence with your logging company. Can we use corrosion log for point indicator? 3-point indicator? No. Corrosion log is the big one. No.
Okay, I think that was the last question. So,
Any question?
yes, I can read one. It says, one is the corrosion could occur while production?
Which one? You have 7? Is the corrosion could occur while production? No. The safety, no. If you warn, if the well is producing and you run anything, you have to shut in the well and do your safety and do that.
There we have another question. Can we confirm that we have a microannulus relying only on CBL or VDL without having an increased pressure pass?
If you have, okay, if you have an high amplitude, sorry, if you have high amplitude and you have uh, casing arrival, a low amplitude, and you have casing arrival. Anyway, the microannulus, if you have, okay, if you are sure that the casing is the cement is the cement operation was very good, and it takes time and everything, and you have free pipe, so it means that you have a microannulus. Just pressure it a little bit, 500 or something like this, and measure it, or you can run USI. Simple. Okay.
Okay, thank you all for attending today's workshop.
What do you think is that if using the penis? What's penis? I'm not familiar with penis. What is a penis? Okay. Physical informed neural network. What does that mean? Sarah? Thank you very much. Unless there is no questions, but that's thank you very much, and see you tomorrow, inshallah, for another two topics. Okay,
Yeah,
Sarah?
thank you, Mr. Hagag, for sharing your expertise and hosting this workshop. Tomorrow we'll be joining at the same time to continue with our workshop. Thank you and see you
Okay.
tomorrow.
Thank you very much.